levels of experience is our recommended practice 001, where we define piping designer levels of competence. And so we looked at this document and enhanced this document when we want to further detail what these levels of certification are. Now, PPD level 2 is all the requirements of level 1, which basically means that you're aware of how to route pipe, but it also includes the ability to check piping routes from PFD to the field, including mechanical completion. And then it does involve some specialty piping that are found in most plants that we don't feel we need to go over for a beginner. And then we need 4 levels of acceptable experience. So we developed a course to teach these skills. And from that particular piece of work, we did learn some lessons. We started testing in 2015. And then we've been in course development since 2018. We had to test before we had the course. And now we're going to revise our tests based on what we've learned from developing the course. In developing, we looked at multiple checklists and how-to articles. And I was a lead author on that. I tried to distill them into topics on quality assurance. And then the PPDAC, the Professional Piping Designer Oversight Committee, reviewed the content before we recorded anything. So I basically had to submit my content to them. What we learned is that there's some general principles to checking piping design documents, also some useful methodologies, and all these things can be taught to other pipers. So let's talk about these principles that we discovered. There's 6 principles of pipe model checking. First is to check against the inherent geometry and topology. Second is capture of design intent. Third is the execution of design intent. Fourth is the preservation of content and structure to another level of detail. The fifth is the traceability to approved data. And the 6th is adherence to CAD and application conventions. So let's talk about this in a little bit more detail. With pipe, there's inherent geometric characteristics of pipe independent of any design application. These include the fact that there's 3D solid shape, there's topological connectivity, and aligned joints. And we can use this to check clash, continuity, and alignment. This has nothing to do with any particular layout. This is just inherent in piping itself. So one principle we look at is our components aligned, and this is a example of several components that are aligned but not connected in the way they're laid out on the screen. And here's a off-center unconnected pipe in practice. Also, this was such a gradual offset that I had to confirm this with the piper, and he did confirm that this offset was correct. It was like 5 inches over 25 feet, but that was a correct dimension. So that was a little trigger for me. As you know, steel pipe and steel sections are usually modeled as swept solids. That's a cross-sectional area that's swept along a path. Some of the components, usually the components, are modeled as computational solid geometry, some say constructed solid geometry models, and these are usually constructed from primitives. In all cases, these solid volumes can be used to check whether pipe is clashing with another solid volume. These are called hard clashes. And of course, you know from design, there can be hard-soft clashes where something it's clashing with can actually be removed for maintenance or enhancement. Here's another visible clash, this time a piping clash with a piece of structure. The other principle that involved in piping is connectivity. Pipes can be thought of as multi-port devices. Pipe is a 2-port, nozzle's a 2-port, and so on. You get in major vessels and their multi-port devices. So here's a line that's not even connected to a desuperheater. It should be, but it's not, and that's a failure of connection. Here's another disconnection seen in a pipe stress displacement inside Caesar. When you run the model and look at the displacement, you see instantly that the Caesar model is not connected. The other thing to check for is the capture of design intent. That is the inclusion of detailed documentation that documents the satisfactory performance of the current document or data sets. In other words, you're putting data in there that shows that that is necessary for whatever you've designed to perform correctly. And these are things like generally accepted practices of level of detail needed. The goal is to document the adequacy of the design and provide instructions to follow-up designers and users. For example, there's a typical equipment description on a P&ID. This is all the data needed for people to judge whether the items on these vessels the vessels here will perform correctly. And here's another example. In this case, it's a P&ID instruction to a fabricator or erector. Another thing to check for is execution of designer intent. The current document must realize the design intent of prior or contemporary documents, such as the realization of streams as lines with instruments and controls, execution of pipe material and client specs and standards, adherence to code, standards and regulations and best practices, and assurances for environmental health and safety. And all these side documents, these are examples of designer intent that you must realize when you perform the design. So we will check things like when we take a process flow diagram, we add instrumentation and sensors and valves that we've implemented the intent of the designer. And then we do a topology check. Everything here that appears on the P&ID should also appear in the piping. And if it doesn't, that's a failure of fulfilling designer intent. Here's another example of designer intent. When they furnish you a pipe spec, you implement the pipe spec in CAD and you design accordingly, insert components according to the instructions in this branch table. Here's another example. Here's best practices. We don't usually put under the rack valve stems pointing into the access space. That's an invitation to disaster. And we don't usually route pipe right through the access space under the rack. So here's some examples. Here's another example of bad practice where the valve stem is pointing underneath the pipe. It's very difficult to access there. Here's a further example of design intent that the actual physical design implements the instructions in the P&ID. Another thing to check for is the preservation of content and structure to another level of detail. Certain content and structure is preserved when you add detail to design, such as unit, process, function, and identity, tag names, equipment nozzle functions, streamline topology. And this preservation is confirmed in cross checks. The BFD to the block flow diagram to the process flow diagram, the PFD to P&ID, the P&ID to piping layout. We do cross checks to make sure this content and structure is still there at another level of detail. So, for example, here's nozzle tags on a vessel data sheet, and here's the actual tags on a P&ID, on the vessel in a P&ID. And here's a PFD source of a stream, a particular stream, in this case, stream 1. And here's that same stream showing up on a P&ID. So we can do these kinds of checks if we're willing to confirm that the original content is preserved to another level of detail. And here's tags on a P&ID that are also tagged again on a ISO. Another thing to check for is the traceability to approved data. All design data must be approved by the client who bears ownership responsibility for the final operating plan. So all design documents must be approved, and the data used must be traceable to approved data. So the traceability checks we have and controls we have are the use of and reconfirmation of approved data, change process with appropriate reviewers and sign-offs, and document versioning and release logs, and so on. I get asked the question, what documents should be on hand when you check a drawing? And that is any document which is needed, that document might be traceable to. Well, we usually implement this as management steps such as built, as approved, as specified, as released. These are release points where we check and make sure that we have approval to proceed to the next step. We often document this in revision blocks on drawings and other places. Finally, is adherence to CAD and application conventions. Almost everyone now today is using 3D design models. It's here to stay. It's not going to go back. We're not going backwards. And so all extracted, reported, and rendered data must remain faithful to the design model. So how do we adhere to this? The CAD or application software that we use imposes data conventions to function properly. So the checks and controls that you would use are, we use application furnished software tools to create and edit models. If we add value and assurance of imported data, we add value to and we assure imported data like scans and converted data. And we assure rendered data such as ISO and exported Caesar models and SAP data sets. And every one of these steps, we have to make sure that the way we've entered the data in the model supports the kind of export that we're doing. So here's an example of where that failed. We had a trunnion support here. You can see it in the 3D model that did not show in a rendered ISO and was made to show later by going back and making sure that it had all the data needed for ISOGen to generate the ISO. Here's another example where a Caesar 2 model is disconnected because of improper coding of a specialty line number. I had to insert this component in. Normally CAD systems have, and there's an example from Revis Bentley, but normally CAD systems have a insertion macro or an insertion routine that lets you insert a component. It's very important that you use the software furnished procedures to do this, because normally the software will preserve the conventions, the data conventions that make the data usable later in the model. Here's another example. In this case, here's a macro generated socket valve from PDMS. And you can see it's got an origin and the out vectors needed for it to operate correctly inside PDMS. Now, even though we've gone over 6 principles of how to check CAD models, there are some methodologies that are also helpful, and I want to review those quickly. Some of these are manual, some of these are digital, but they are things that checkers use to do checks. And some are easily done on paper documents. Others are best done in digital models. Some cases they can be automated. So let's look. There are things like checking grammar. You can read things aloud and check for speech flow. You can see if things are correctly rendered by going and finding things in the rendered document. You can check for connectivity by doing a walkthrough. You can check for completeness by item markups on P&IDs and other complete documents. You can check for accessibility and clash using 3D viewers, pan and zoom and rotate. I found to my surprise that many designers inside CADWorks, it's so easy to view the model that they often don't run clash checking because they can just see instantly in the model if there's any clashes. And then data assignments. You can use this with color coding and selective viewing. These are just examples of different methods of checking. So one application of this is using a narrative method on checking P&IDs, and we cover this in the course. But many people do narratives on their P&IDs. Some people do walkthrough commentaries, process explanation, HAZOPs, they write procedures. Every one of those narrative walkthroughs of the P&ID is a checking methodology as well. People used to say in HAZOPs, they would find so many mistakes in the HAZOP that it would pay for the cost of the HAZOP itself. Here's another example of where you can selectively view piping data according to a spec and line number, and we see an orphan component is not on the line. It shows up in the selected viewing. This is something you can only do in a CAD model. We often do manual markups, and here's some examples of color methodology for marking up a hard copy, but this is a manual method. People use it every day. So what are the takeaways today? I've gone over what we really try to address inside PPD level 2, and which is piping assurance. It's a brand new course for us, but it did teach us some lessons, and that's what I went over today. I've also identified 6 principles for checking. Checking using the inherent geometry and topology of pipe itself, the capture of design intent, the execution of design intent, the preservation of content and structure to another level of detail, and the traceability to approved data. And finally, the adherence to CAD and application conventions. And then at the end, I went over some of the common methods used by checkers to check these drawings. I'd be happy to take any questions from the audience. Are there any questions?
I think, Bill, if anyone has a question, they can just pop it into the chat, and then we can address it like that if they don't want to, speak lively. So we can maybe just put it in the chat.
By the way, I've arranged with Chempute to send you a copy of the slides. Make sure you're registered and with them to get copies of the slides. And I'm going to be around for just today and tomorrow in Durban, and then I'm giving another talk next Thursday in Johannesburg. So any questions? So I dazzled you and you're all stunned and into silence. That used to be fun, but anyone
see we have a question from Denver. Denver is also one of our local engineers. I think Denver works for Sassel and Natref. Okay. So go ahead, Denver.
Where do I see the question? Okay.
You don't have to see it, Bill. I'm not shy to talk.
Okay.
Okay, so Bill, one of the things I've been pondering, and maybe I can get some guidance from you on this, is I do a lot of work on the project space, on larger projects, and we often use a staged approach, or the stage gate approach to implementation. So a little preliminary development of the model in the feed stage, which we use to refine our costs, apply for capital, and then move over to the detail stage. So the question now that relates to what you were going in here, let's just say in the feed stage, we're assuming we're sitting with a nice package. We've done quality work, checked most of what you have done there, because if we didn't, then our cost is off. But we move into contracting, and we go to 5 bidders. One's using Navisworks, another is using SmartPlan 3D, and maybe the third is using Autodesk Inventor. am I going to run into any trouble here if I choose somebody with another software and I offer him the seed files from whatever we used in the previous phase? Can you share your thoughts on that?
Yeah, personally, I always see it at great risk to deviate away from the main modeling software. It's not that I'm pro any particular modeling software, but there's always a great risk in moving to another package. Some of these packages export very well, but you do add a quality assurance step every time you do an import. If you stay within a vendor's package, and even vendor software can have bugs, it's still a little bit easier, a little less checking to stay within their packaging conventions. It does mean you have to become a power user in one application. That being said, we're in the business of importing data from wherever we get it, like a scan or something else, and adding the right added value so that it operates correctly in our modeling situation. Anytime you take something out of the model and you add a lot of value to it in another application, it's hard going back. In fact, you have to redo it to go back. So I do favor staying within the modeling domain of the main model software. I do favor that, but in some cases you're just better off. The operator's more familiar with another environment, and then you have to get into the export and reconciliation business, the error checking and reconciliation business, and that's the worst kind of industrial accident is to make a data mistake because you don't see it. It does, data doesn't import completely. You don't see that something's missing, and you go on fat, dumb, and happy working with the data, and you find out later it's defective. And I have been caught like that many times. So it does have its dangers, but that's a calculated risk.
But in terms of your files, can you import from one? So let's just say I started off in Smart Plant with one consultant.
Yeah.
I go out in competitive bidding, and I move over to somebody else without checking that he's working with Autodesk. Is it possible in all scenarios to export or import that previous file into or model into the other software, or will it require a redo or development from scratch?
Well, it depends on the package. I mean, I look at a lot of packages that'll work with, say, an AutoCAD layout plan, and you can add nozzle locations and other things, and you don't have to add a lot of value to gain the compatibility you need with the overall model. A lot of people, like vendors, will supply AutoCAD drawings, and you can just add enough added value so that it'll play correctly, say, in CADWorks. In all those cases, any defect in the import is going to be your responsibility. And it does take a little bit of QA to make sure all the nozzles are there and they have the right properties and they all contain alignment. Most packages do have tools to aid that import. Now, I'll have to defer to Chempute to talk about what CADWorks does, but most packages do have some kind of import tools. And remember, we get external data all the time. We get field scans. Those field scans look really pretty and they're really nice, but they don't have nozzles yet. So you have to add value to that data anyway. So you're always in the business of reconciling and adding data so that it'll play correctly in the final model environment you're going to use. Does that answer your question?
I just want to expand it a little bit further. Maybe it'll
Sure.
add value for people in the project space whose main purpose is to manage not just quality, but cost. So you're basically agreeing with me that the risk is not just on quality, right? But if I come to you as a consultant and I tell you, listen, I've got everything. I've got a package that you can treat as relied upon information, but you find out then it was done by a different software. It's not going to be fair to me. I mean, or do you see it then as a fair enough consideration that we should take, that whoever you give it to that is new using different software will then be required to an allowance should be made to give this guy a chance to then incorporate or import that and refine it, to ensure that it is now totally compatible and, of the same level as the previous model done in the different or using the different software. That I'm just going, or my concern here is the time aspect of it as well. I don't think it'd be fair to just go out and bidding. We change parties, they're using different tools, and we don't take or make an allowance for this.
Well, if it was my job and I was running the job, I would always allow hours to quality assure what has been imported. I would, sure, you want to keep the files in native source, but you want it to play correctly. I mean, if you have say I dealt recently with somebody that had done some work in Rebus, and they'd done a lot of modeling of a boiler, and I made the mistake of asking to import their piping model into Caesar. Well, it came in and looked great, but a lot of information was missing that I didn't catch. The nature of the stops, the nature of the supports were missing. A lot of stuff came in, and I got bitten later by finding out that their data was not a complete and correct import. So you have to allow, it would be stupid to not allow for hours to quality assure what the vendor wants to import. Now, after that being said, it's almost always faster to import the data than to re-enter it. Because when you re-enter the data, you introduce new errors, and they have to be caught. So it's anything I can import, I will take, but you have to allow hours to quality assure. It'd be silly to take it as completely correct, no matter how proud the supplier is of what he's created, no matter how wonderful he says it is. And I'm sure it's been quality assured on his side, but there are always defects in the translation when it's imported into another situation. So I would be very cautious there and always allow hours to double check that things are playing correctly. Does that answer your question?
Yes, thank you.
Okay. Anybody else? Okay. Any further questions, you can route through Andrew Taylor, and or if you want me to call you directly or visit you and discuss something with somebody else, that's your call. Please coordinate with Andrew Taylor. I thank you for attending today, and with that, I'll end the seminar.
Thank you, Bill, and thank you to everyone who joined the forum and the presentation. We will make all the slides available as soon as the call ends and the recording. As Bill said, we are available for any questions afterwards. You can either contact myself or Andrew. I'll hang on to the call a bit longer just to see if there's any other questions or late questions. But thank you, Bill. It was very informative.
Okay, thank you.
Lian? Lian?